Thank you. Thanks, Phil. So I'm glad that almost all of you saw the keynote this morning. It sort of preps you for some of the stuff we're going to show. We got a lot of attention from showing the cloud rendering service, which we announced today officially. We've sort of been teasing that for a while. But how many of you in the audience are familiar with Octane Render prior to us showing the cloud? Okay, so a good number of you. And how many of you are familiar with LightStage in general? Okay. So these two technologies for us are pretty key. They're converging, in fact, towards a pipeline that we see as being really important to both films and video games. I think the case for filmmaking is pretty clear. But so we're going to start with that, and then at the very end we'll sort of get to how this affects video game development. And for us, the cloud is really also the place where these two technologies converge. LightStage has a lot of data. Octane can render a lot of data, right? So the idea is that in the cloud where you have unlimited storage and unlimited rendering power, we can provide a service that really makes these things much easier to use. I'm going to start by talking a little bit about Octane for those that aren't familiar with it. It's the very first GPU unbiased spectrally correct render. And so what spectrally correct means is that it is physically accurate. It's like running a physics simulation. When you're not spectrally correct, things like gold, for example, don't render right. You're going to have light bouncing around gold, and it's not a mirror. It actually changes the color of light. And so if you miss those little details, you're not going to get a render that looks as real as this. And our users have been beta testing Octane for about 2 years. They've been creating some of these fantastic renders that you're seeing here in a matter of 10, 20, 30 minutes, maybe an hour or two. And they do it on their own GPUs, sometimes on their laptops that are essentially equivalent to what we have here that we're presenting on. And it's exciting. It's really been an interesting development to sort of see the quality that we can now deliver to an end user that has a single GPU or a couple of GPUs. Octane really, I think, pushed the boundaries of what you could do with rendering. These are, the caustics that you're seeing here. Caustics are light passing through a liquid or glass, and then having that color and those lens effects show up on a surface. What you're seeing here is typically not even used in final renders, like Spider-Man and Cloudy with a Chance of Meatballs that are done using a CPU render like Arnold, which I think is incredibly high quality and can do caustics. Well, they turn that off because CPU renders typically just take too long. You don't want to wait 40 hours or 10 hours. And Octane has really been able to deliver this kind of quality even on a single GPU for in a matter of minutes or under an hour. And with the cloud service, as you guys are seeing, we can deliver that now in a second. And I want to really talk a little bit about how the cloud service is going to impact these kinds of renders. There's a lot of users that are very comfortable working on their systems at home. And then you have a lot of users that are looking towards building rigs and building their own render clusters. And this was before we announced the cloud service. And I think what's going to happen, especially when you get to these kinds of renders that are, that do sort of push Octane to its limits and take a while. I mean, this render probably takes closer to an hour to render, just to get all the noise and all the other pieces out of the render. When you're doing physically correct rendering, it doesn't work like the older style renderers. I mean, it does, it really does calculate the physics of that scene. And until it's finally done, you may get speckling. It's almost like exposing a photograph, right? You need to get in enough light or else you're going to get a lot of noise in a low exposure negative. So as we look towards, how we want to provide a service that is, really quick and fast, the cloud really is that solution. I'm going to show a few more scenes. I mean, obviously for automotive stuff, Octane's fantastic. These are still, earlier versions of Octane Render. So one of the more recent additions that we added was the ability to do, much more interesting things with glass and with water and even fog. And also, again, you get very interesting dispersion effects, scattering effects. Those were added about a year ago. And as we sort of come up to some of these scene renderings, we just, this about a year ago added instancing support. So it's very easy to create forests and cities that have thousands of unique objects that are based off the same base mesh. And that's very important for a GPU render like ours, where you want to have, let's say, the base mesh of a tree stored in memory once, and then you can replicate that many times, change the materials, change the size, but essentially you're not using any more memory. And talking to NVIDIA and sort of looking at their roadmap, it does seem that we're not going to really have a problem with memory by the time we get to Maxwell. There's going to be out-of-core memory access, which is going to be possible on chips in 2014. Already this year, we're going to see GPUs with 12 gigabytes of RAM, which is great. That's enough for us to really fit in scenes like what we're showing today with the Transformers models. We can fit 2 of those robots in 12 gigs and really do an interesting environment around them. And that's enough for us to really start doing full movie production and renders like the stuff that we were talking about doing with Josh for Fantastic Four. This is a great render. I mean, this is on our gallery. This is one of the more recent Octane renders, and it's showing scattering of light through the atmosphere. That's very time-consuming and intensive. Skin rendering also can be very complicated. But this is something that really I think we excel at. When you're starting to deal with the physics of light scattering through a volume, that really does kill a lot of unbiased renders, especially on the CPU. And Octane is able to do this very quickly. I was testing this on the rack, and it renders in basically a few seconds. What we were showing with the transformers was rendering in a split second. So, really, when you're on the rack, none of these scenes are really going to break the render. It's not, it's not that complicated. One of the things that's very interesting with rendering in the cloud is that you can actually start looking at things like 8K renders and stereo and all these things, and those really can almost be done for free, because when we're spreading rendering over larger frame buffer sizes, the number of samples that we're rendering in Octane can be spread out over that larger frame, and the quality is still very high. In fact, when we're rendering a smaller image, we're actually just squeezing the same number of samples into a much smaller frame, but you're losing all that spatial resolution for no good reason. So I think when people start moving towards the cloud service, they're going to start using 4K and 8K renders. That'll be the default. There's a lot of stuff that we were showing just in terms of the pipeline, right? I mean, we were showing the demo this morning. We were running 3D Studio Max in the cloud from a data center that was, 600 miles away. So there's a lot that's moving to the cloud besides rendering. Applications, workflow. I think that, we can speak a little bit towards how we imagine our specific service connecting with some others out there. We want to really be an extension of the GPU, right? So we're not necessarily going to be focused too much on storage of files or documents, but we will handle things like, being able to virtualize apps. We've worked very closely with Autodesk and some other partners to get that to happen on the cloud. And so you should be able to connect to our data center or others that are potentially hosted by third parties that have this system hooked up, and you'll be able to render with Octane and use other apps on those systems that can provide you a workflow that's entirely in the cloud. And I do think that that's the future. I think that there is, especially as data for rendering becomes bigger and more complicated, and you want to collaborate and share with others, especially if you're working on a big production or even a medium-sized production, right? I mean, that's where the cloud really makes a lot of sense. And so for us, when we look at where the future of all this is going, go up here. I mean, I'm sure we're testing 16K renders. Why not? I mean, the cloud can, we can render that without it. It takes about a second longer to render that than it does an 8K render. So, for me, I think the insight is, the spatial resolution doesn't matter. Being able to render stereo or even, really a lot of views, right? That's where cinema is going as well, where you, instead of rendering left and right eyes, you can render many, many, many views. And that's something that we'll talk about a little bit later. That gives you some very interesting capabilities as far as being able to refocus and do depth of field effects totally in post, but without losing the quality of an unbiased render. And I think that's where the power of cloud rendering really sort of eclipses anything you can do even on a local cluster. With Octane, we have a lot of dedicated users that are always going to want to be able to render locally, and that will never go away. The cost of Octane is $199. It's very cheap for those that aren't familiar with the price. It's designed to, we wanted to sell it to a large number of people and not have it be this really expensive render that only professionals can use. We wanted to get people that maybe had never experimented with rendering trying it out. So while we're obviously targeting very high-end films with it, we also imagine the very same technology could be used for hobbyists, and at $199, that's totally reasonable. What's interesting about the cloud service is that we don't have to sell Octane for anything. You can basically log onto the cloud service and you can pay for each render and still create something amazing and probably do it faster and better than what you could do with Octane today on your own machine. And that's something that I think is incredibly compelling. We're trying to figure out the right pricing for that. And so a lot of questions we got after the keynote was what does this cost, right? And so we're going to get into human rendering and all that stuff. And that's how Untitled LightStage. Before we get into that, I'm going to talk a little bit about the pricing model that we sort of we're starting with. So the cloud service is going to be in beta in a couple of weeks. Josh Trank is our first customer, really. I mean, we're obviously doing tests on Fantastic Four and other film projects. But we're going to start letting Octane users, just as we have other Octane plugins and the Octane standalone application itself, we're going to start letting them log onto the cloud service and try it out. And the entire Octane application will be in the cloud. We're going to provide a pipeline for users to upload their data or bring in things like Dropbox or potentially Autodesk Cloud Documents, right, where you can have your 3D model stored, and then that would be a way for you to tap into this. There's going to be an infinite number of ways for the Octane Render service to be used, and it'll probably be integrated in other applications. It won't just have to be through us, but that is sort of how we're beginning, to test it. We have to start somewhere, and I think the pricing that we've sort of settled on is, if you look at the VGX cards, sorry, they're called Grid now. When we started working with NVIDIA, they were called VGX. They're pretty powerful. They're about 75% the speed of a 680 per GPU, and we're going to be providing, just in a raw number, the maximum cost you'll spend to render with one of those cards for an hour would be $1. So about $1 an hour for one GPU. Now, if you were going to use 112 GPUs like we did this morning to render that Starscream transformer scene in a second, well, then it's going to be $112 an hour. But remember, it's rendering that in a split second. So that's where the pricing becomes very interesting. There's no real reason why you just can't use the entire rack or the entire cluster and then get to the next user. We didn't talk in the keynote today about the architecture behind our rack, so I'll touch on that a little bit. It's hooked up entirely with InfiniBand, high-speed InfiniBand. So there's really no speed difference, no latency, right, between any of those 160 GPUs. There's actually more than 112. We weren't using all of them this morning. But there's 160 GPUs per rack. We can have 10 racks in a data center without really stressing ourselves too much. That's 1,600 GPUs, and they could all be rendering one frame. We probably don't need more than a few hundred to render a high-end film like Transformers. But the interesting thing is that when you're done rendering a frame, those GPUs are then free, and they can be used by another user. And those users can then really just pull from that elastic cloud of GPUs to render what they need. And of course, it's expensive. If you want to render everything in 4K and do that for an hour, well, you're going to end up spending hundreds of dollars. But if you just want to see what a scene looks like, you can elastically switch from using a few GPUs to using that 100. And if you remember the scene I was showing this morning, it was actually a little blurry for a split second as I was moving the mouse. And then as soon as I let go, it resolved. And the reason for that is that I don't expect users to want to necessarily, when they're moving the scene around or playing with lighting, they don't necessarily need 100 GPUs for that. It's more when you want to see what the final frame looks like. And that saves a lot of cost. And that's what's going to be accessible to the average user using this service. There's going to be high-end customers like the movie studios that will want to have everything rendered perfectly while they're looking at a film. I mean, directors like Josh will have that. But that's not the only way the service will be used. So again, when we're talking about $1 an hour per GPU, that's the maximum cost. If you think about how this would relate to Amazon's Elastic Compute service, for example, you've got on-demand pricing, you've got reserve pricing, and you've got spot instance pricing. And I think what's interesting is we can certainly adopt a spot instant pricing model where if there's GPUs that are just available and not being used by anybody, those could be provided at a much lower cost. So the way that we're probably going to be providing this to users is through render credits, because the render credits mean that you will have a certain amount of let's say $50 buys you 50 render credits, and at the minimum that will give you 50 GPU hours. It might give you a lot more, and that's why we want to sort of move to that sort of model rather than saying it's going to be $1 an hour. That'll be that'll be the worst case scenario. But I think users will find a lot of value in being able to have a flexible backend that can adjust the price based on how many users are using a particular rack. And so I think that's an important piece as well that we're pretty excited to roll out. So here I'm starting to show renders that are based on human expression and skin and the like. And so we added, as I was saying earlier, we added scattering to Octane, subsurface scattering, about a year ago, specifically to deal with things like wax, water, skin. And that's really where LightStage comes in. Now, these are not LightStage scans. They're models that were done by one of our artists, and we tested it in Octane. There's some fantastic work being done by our users. I mean, this was just done in ZBrush in 2 days. It won an award, and it's all done in Octane. And it really shows how good an artist can be when they're just sculpting stuff. I mean, it's a fantastic piece of work, and it's actually, right now, it's our splash screen. And it's astonishing to sort of see the quality that one artist with ZBrush and Octane can put out. I mean, this is good enough to be used in films. So, this is one way of doing, skin rendering and characters. But, you're limited really by the artist, right? I mean, you have to have a good artist to be able to deliver that. So what we want to do is we want to provide a mechanism through LightStage. Obviously, our big customers for LightStage could be studios, but we want to provide a data set of data that end users can use to start building characters and assets that can match this quality. So that really does bring us to what LightStage is all about. And you guys saw a little bit of that this this morning during the keynote, in terms of what the final product looks like. It's essentially, it gives you very high quality skin and head rendering. And the process is interesting. I mean, it is like the Brundle fly kind of device, right? You sit in it, and a ton of lights spin around, in terms of being able to being turned on and off. This is our COO, Clay, who's actually in the audience, being scanned. And once you're done, and the scan, we're slowing it down. The scan's only a few seconds, but the quality of that data is phenomenal. I mean, it gives you wrinkles, it gives you perfect, pore level, resolution meshes, and it gives you that in motion. It can give it to you statically, and it also gives you something else that's very important that separates the LightStage from every other scanning process out there that I've seen, and that is it gives you the full BRDF, the reflectance properties of skin. And if you don't have that, it's very hard to render correctly what skin looks like. You can get close, and there's some great artists out there that can do that, but it's much simpler when you actually put the actor or the subject inside of the LightStage, and you get this. This is now Octane rendering LightStage data. So we're dedicating a huge number of resources towards bringing Octane and LightStage together so that this is what you get right off the bat. There's a lot of work that was done with LightStage data for films, and we can go through some of the history of that. And it was always an expensive process. It was always a difficult process, and it still is. I mean, we've been doing films all the way up until right now. And one of the things that we've always seen is that the data isn't, it's either expensive to store or it's expensive to render, or somebody has to write, new tools. And LightStage is actually a pretty well-known force in the visual effects industry. Paul and Tim, who are part of Otoy and who built the LightStage technology, won an Oscar for their work, and they won an Oscar for all the films that LightStage was used in. And the gamut of that is impressive. One of the earlier, adopters of LightStage was Sony ImageWorks. So their work on Superman Returns, you can see the digital Superman and the real version. That was back in 2005. So LightStage has been around a while. It predates Otoy's involvement. Actually, it was a research project at USC, and it has now sort of become a commercial entity through Otoy. Spider-Man 2 was another film that really utilized LightStage properly. Again, done by Sony ImageWorks. You're looking again at the real Alfred Molina, the CG version on the left, and the shot of the end of the film, the money shot where it was used. And it looks so good that you can't tell it's CG. And that's the beauty of LightStage, is that if you just use the data and you don't do anything else to it, you'll get a perfect render every time. As we sort of move forward in time, Benjamin Button, which was worked on by Digital Domain, which won an Oscar, that was also the old Benjamin Button was actually a sculpture done by Kazoo, and Fincher hired him to sculpt this old version of Brad Pitt, because you couldn't get Brad Pitt to look old, right? You have to reduce muscle mass. You can't do that to the real Brad Pitt. But we scanned in the head, and basically Brad Pitt then animated it with Image Metrics providing the sort of the pipeline for capturing the motion data. And we still work with Image Metrics. And there's a lot of interesting pieces that you can sort of put together with LightStage at the center of that. As we get a little bit further, then you get to Avatar, and that's one of the reasons why LightStage won that Academy Award. So there's a lot of scenes in Avatar that use LightStage. One of the more memorable ones, hopefully not spoiling the movie for anyone, but when Sigourney Weaver's at the end in her human form and dying, that's a LightStage capture right there. And I remember I was, when Jim was first starting that movie, I had a meeting with him, and I told him what LightStage was all about, and it was with Joe Letteri, basically who ended up being the visual effects supervisor for Weta on that, and it was really an interesting way of sort of seeding LightStage into a big production, and it ended up working out really well. And it's still interesting to sort of think about how that could have all been improved, and that goes for rendering as well. But we're working towards making that something that not only is simple for huge directors, but also for end users. And LightStage capture is not something that necessarily requires a huge LightStage. We can get to that in a little bit. Before I do that, though, I want to discuss the latest film that used LightStage really in a nice way, and that was Avengers. And there was one character in particular, if you saw Avengers, that you might think this would be perfect for LightStage, and it was, and that was Hulk. So we ended up scanning the heads of every single hero in that film, and Loki. And the only person we didn't scan, I think, was Nick Fury. So everyone else had a CG LightStage head made of them. But Hulk was obviously the most interesting one, because it really does speak to one question I've always been asked about LightStage data. Can you LightStage something or someone and then turn them into something else? And so the answer is yes, you've got Hulk. And that is actually very heavily dependent on the LightStage scans that we did. It's very exciting to sort of see. So you got here the LightStage data on the left, ILM's digital recreation with the LightStage data on the right. And that was very important for them because they had to take the LightStage data in its rawest form and rebuild that in their shading system, in their pipeline. And so we need to basically provide an automated way of doing that in Octane, and we are getting very close to that. What you saw with Clay's head was basically that first recreation of that. This is, again, just showing the CG Hulk from using the LightStage data. I mean, it's an exciting shot. And the poor level detail that you get is only really possible with stuff like LightStage as the source of that. I mean, if you see this shot, I mean, it's a great shot. And I think that when you saw the impressive real-time face demo, you also saw a lot of that detail that came from LightStage. This still isn't using all the lighting layers that we can capture with LightStage, and that's because probably there's memory issues. There's also the data that we provide is there needs to be a common file format. So we're working on introducing that in Octane, and it'll allow you to do very complex renders with this kind of quality. There's Mark Ruffalo in our LightStage in Burbank. So we have an office in Burbank that's dedicated just to performance capture, and this is Mark in the LightStage for that day that he was in our studio being captured. This, by the way, is what the raw data looks like before you add all the other lighting information. It still looks really good, and that's very similar to what we did with the Octane Render for Clay. And you can see here other behind-the-scenes work in progress done by ILM as they were working with our data. And that brings us to again the pipeline that we're sort of converging towards with Octane and LightStage combined. And so here is Clay's head. You saw the scan earlier. These are the different pieces that come out of that scan. You've got diffuse, specular, and normal. So that's the very simplest LightStage. It's not that different from a video game asset. And I think that you'll see in the next few weeks, you'll see some major game publishers announcing that they're working with LightStage or they're building their own LightStages. I mean, it's definitely something that we're going to be pushing to commercialize in a big way. It's very simple to use that in old-gen consoles just by using just this little bit of data. That's no different than what you get in current-gen games. There's a lot more data that can be used. Octane can provide that, but even for older engines and older rendering systems, this is still great stuff. When you do use it in Octane, though, you get this quality, and this quality is great. I mean, there's no setup required. We took the skin, the shader, we put it on Octane's live database, which is a database that's accessible to every Octane user for free, and everything that we build or other users build can be used by others in the community. And a big part of Octane's appeal is that there's a huge community of users. Even it really grew during the beta period over 2 years, and they help each other out. I mean, if you go on the forums, it's better than any documentation or any set of tutorials that we could make. They really do help each other out, and we want to seed that as much as possible. So, by adding things into that mix, whether it's the cloud service, whether it's LightStage data, whether it's LightStage shaders, that's really going to accelerate the ecosystem that we've seen burgeoning, in the last 2 years. This is an 8K render with LightStage, and this is another newer iteration of that. And I think this is one of my favorite renders. I mean, this is really nice. When we posted this, it got a huge amount of attention. It's remarkable not just because of the quality, but also because of how simple and easy it is to bring this data into Octane from a LightStage scan. And one of the things that we imagine doing as we go forward is actually scanning a lot of generic people, right, and having a number of heads and different shaders that we can then provide through LiveDB and let users start building characters and scenes and humans with this kind of data. So I want to talk a little bit about where all this is going, because we've shown a lot of how this can affect films and rendering in general, but there's a real-time aspect to this. I mean, if you saw the presentation this morning, I mean, the great thing is that you actually get this feedback in real time. You can move the scene around, and I was saying it's almost like a video game, right? I mean, we can really see these renders, at 30 frames a second, and with the cloud, that is pretty easy to do. I mean, it's something that is within reach, right, to get path-traced rendered graphics. So we have another piece of technology that we've been developing called Brigade. It initially developed totally separately from Octane. It was a separate team, and it was developed by Jakob Bicker, who is very well known in rendering circles, and his focus was on speed, whereas Octane's was on quality. So my thought is, as trying to bring these two technologies together, is can we actually get the speed of Brigade in Octane? And we have. And so what you guys were seeing this morning was actually the very first version of Octane that has some of that Brigade code in it, where we can move that transformer around and the scenes around, and we get this dynamic realism in there. But we didn't really get a chance to talk about Brigade or show Brigade this morning, so I'm going to show a video it's just a tech demo. It's nothing too crazy, but it really is designed to show the speed of Brigade. And you have to remember, when you're talking about ray tracing or path tracing, the hardest thing to do is change the scene. It's actually fairly easy, and a lot of renders do this, right? When you have a static scene, just to let it render, and it comes out looking really nice. It's very hard when you got things moving, because you have to change. It's not like sending triangles in a traditional video game. You've got to recalculate everything so that the ray tracing happens instantly. And so this is Brigade. This is actually in-scene changes being done. There's a little bit of noise. I mean, it's not running on a whole rack. It's just running on a couple of GPUs. But if you look at that, I mean, this is video game physics, right? I mean, there's nothing that we can't change in the scene. I mean, in fact, this is a live demo. One of our tech guys is driving the car around, and you have bullet physics. You have everything. And we're still able to do ray tracing in real time and path tracing. And that's pretty exciting. I mean, that's never been done before. I've never seen this be achieved. So we really are looking at getting this from both ends, right? We've got Octane for films and for high-quality rendering, but then we have Brigade for game engines. And we can combine those a little bit further. I mean, this demo doesn't show this, but we can actually have Octane do all the baking and all the lighting for the world, and then just have Brigade do local lighting, right, at a little bit lower quality, but at this speed. And that's where you will see cloud gaming start to really become very interesting, where you will be able to not worry about what the user has, or what the limitations of a particular GPU or console might be. I mean, you're just going to be able to pull in resources for Brigade, for Octane, do whatever you want. And I think that this piece is really critical, because it does show, yes, you can actually have a first-person shooter that's path traced. And a lot of the comments, I mean, we have a blog about Brigade, and people have been following it for a while. Do you guys want to see the video again? I can play it again. All right. Let me click back and see if we can do that again. Yeah, I mean, it's an interesting thing to see. We haven't really shown this publicly yet. We've been teasing Brigade, we've been showing little demos and stuff, but we haven't shown a full, physics simulation running in it with game engine physics and stuff. And it is pretty cool. I mean, it does, what we imagine for Brigade is not to go and compete with Unreal or Crytek. This is a replacement for DirectX or OpenGL. I mean, really, we can also dial back the ray tracing, right? And so we can just have pure, widget style ray tracing, which doesn't have any of the noise, and you can then basically replace OpenGL or DirectX with Brigade, with all the dynamic qualities that you get from what you're seeing here. The difference is you actually have, at above 10 million polygons, ray tracing will beat rasterization, right? So if you're going to have enormous scenes with just giant amounts of trees or whatnot, I mean, at some point you're rendering, and Carmack pointed out, you're going to be rendering more triangles in your pixels. So that's where ray tracing really takes off. And it's not going to be that useful necessarily for less than 10 million polygons. But when you go above that, and most games today are, that's where you're going to see that convergence point where ray tracing is going to beat rasterization. The other thing that we can do very easily with ray tracing in the cloud is we can divide things much more easily. So you can actually have many, many, many users ray tracing on one GPU. There's no real cost for the geometry for the to be re-rendered. So if you're doing 6 views in a GPU, you actually have to send the geometry down 6 times, and that's a 6x penalty for the complexity of the scene that you don't have with path tracing and ray tracing. This is all getting interesting when you start to think about what you could do with path tracing and ray tracing, both for Octane and Brigade. And one of the things that I've always wanted to see happen is holodeck, right? I mean, you saw that if you guys are Star Trek fans. I don't know how many of you guys are, but remember the very first episode of Star Trek: The Next Generation in 1987. I remember watching that, and they had this thing called the holodeck, which was basically a VR room. You go in there, and it's just, the world is real. You can touch it. It looks completely immersive. And, that's something that seemed pretty far off, 25 years ago when that first aired. But we're getting closer to that. And I have a very, I'm really passionate about holographic displays and holographic technology. There's a lot of pieces that you have to get working to get a holodeck to work. So one of them is the rendering. So what you guys saw today with Octane this morning, we can render almost anything that looks real in real time. I mean, that is, we can take 100 GPUs to do it, we can take 1,000, we have the compute power, and it's not that expensive. If you imagine the holodeck is going to be something used maybe for military simulations or theme parks or things like that, you could imagine a GPU render farm that can power that. What's interesting with path tracing is that you can then generate all the rays of light. I mean, a hologram is very simple. Instead of having a pixel that is just one color, every pixel has 250,000 subpixels that shoot out in all directions. So wherever your eye is, you're going to see, like a white light hologram, you'll see a perfect a perfect representation of the scene that's in the holographic image or display. And Octane can render that. I mean, just like I was saying that 8K isn't really an issue because you're just taking samples and you're spreading them over spatially. Well, you can take those very same number of samples and you can divide those holographically so that instead of just doing one 8K image, you can actually, if you're rendering at 16K by 16K, you can pretty much with that generate a 1K by 1K image that's holographic and just have all of the light rays organized in such a way that you can actually drive a holographic display. So the key part is, what's the holographic display going to be? That doesn't exist just yet, but we're getting closer to that. The very first thing that we're experimenting with is we're partnering with a company called Zebra Imaging. They create great stuff. I mean, this is one of their this is how they currently do things. They do holographic printing, but it's digital, right? So you basically can send them a file, and you'll be able to send this from Octane Cloud right to Zebra Imaging, and Zebra Imaging will send you back for $300 one of these, which is a holographic printout of whatever you send it from the cloud. So all those renders you're seeing in Octane, this could be a hologram. And there's a lot of uses for this. Obviously, it could be used for for point-and-purchase displays. But more importantly, from the technical perspective, it shows how Octane as a renderer can then start to drive what we might see in a holodeck. There's 250,000 subpixels in every pixel in that hologram. And it is digital. It's not done the old way where you have to, you have to have a monochrome holographic print made and have the subject stand still. If you LightStage a person, you can then put them in Octane, render them, and then print them out as a hologram. And that's pretty cool. There's a lot of potential there. Zebra Imaging also, by the way, is working on motion displays, right? They can do motion holograms. It's not as far along. It's not a commercial service yet. This is. But it points to I think, a future where holographic display technology will be very real. And it's not 50 or 100 or 200 years in the future, like on Star Trek. I mean, it's within the next decade. So I want to close by showing something really cool. And this also is coming out of Paul Debevic's lab. We're working with him on something that is really at the tail end of all this, right? And we've got LightStage capture, we've got Octane to render, we've got all sorts of other stuff happening in the cloud. And the last piece is the display technology. And I wanted to close by showing something really cool that is only in the prototype form, but it's something that I think you guys will dig. Actually, this is another Zebra Imaging render, so I'm going to skip to this. So this is a holographic display. We're building one in our office. It's a little bit bigger, but this is the very first iteration of it. And it's being driven by LightStage data. And there you go. I mean, it's the size of an iPad, but it is a holographic imaging system, right? That you can walk around. There's no glasses needed, and it's purely. It's a prototype. I mean, it's still the lighting and everything can be better, but it's a good start. Do you want me to play it again? All right. Let me do that. Yeah, I mean, this is exciting. So there's a lot of work that's being done. Paul's building. I mean, I don't want to steal thunder. I mean, he's building a bigger one. We're building actually a smaller one because one of the things that I want to see happen with a holographic display is if it's smaller, you're going to get to a point, right, where the holographic rays are going to allow you to look at the hologram. And something people don't understand when they're doing just left and right stereo 3D rendering is that the eye doesn't just see two images. It sees way more than that. If you send more than two images into the pupil, what happens is the eye then can focus on that image, and that is a huge reason why reality looks so real to us. It's never going to happen if you're just sending one image to each eye. So by making that a little bit smaller, we can converge the rays a little bit, and that's where you're going to be getting that effect. So that's probably the next step is a smaller version of this. Paul will do a life-size version, and then there's other technologies that we're really looking at that could also be very interesting. There's a lot of lenticular stuff that's coming out where the lenticular displays are getting really tiny. There's already 28 view holographic displays made by Demenco. But this stuff is very interesting. This stuff is done with an array of projectors on a mirror, and that gives you, it doesn't give you the same resolution limitations of lenticular displays. It does allow you to just have however many projectors you're willing to throw at the mirror. That's how many rays of light you can really spread out. So I think this covers the end of my slide deck. I mean, I'd love to answer some questions and comments, anything that you guys want me to delve deeper in, I'd be happy to talk about.